This video provides an introduction to drawing Lewis structures. Lewis structures are used to show the arrangement of valence electrons in molecules. We will use chemical symbols, lines, and dots when drawing Lewis structures. The lines represent bonds, each consisting of 2 bonding electrons, and the dots represent lone pairs. During the course of this video, we will draw the Lewis structures for simple molecules, multiple bond molecules, multiple central atom molecules, polyatomic ions, and incomplete octet molecules. We will use the NABL method to calculate the number of bonds and lone pairs needed to complete the Lewis structure. We will start with an overview of the NABL method. N represents the total needed electrons. It is the sum of electrons needed for all atoms in the compound to be stable. The majority of atoms need 8 electrons. Exceptions to the octet are hydrogen, which needs 2, beryllium, which needs 4, and boron, which needs 6. A represents the available electrons. It is the sum of the valence electrons that the atoms in the compound contribute. B represents the bonding electrons and is the difference between N and A. N minus A gives you B, or the bonding electrons. We're going to divide that number by 2 to get the number of bonds, and we use lines to represent bonds. So this number tells us how many lines will be drawn in our Lewis structure. Multiple bonds will be used when and where necessary, but note, hydrogen and halogens can never have double or triple bonds. They are only able to make single bonds. L represents the lone pair electrons, and it's the difference between A and B. So A minus B will give us the lone pair electrons. We're going to divide that number by 2, and that's going to tell us how many lone pairs that we're going to place in our Lewis structure. We will place the lone pairs on the central atom last when completing the Lewis structure. Hydrogen will never receive lone pairs. It achieves stability when bonded to the central atom. Remember, it only needed 2 electrons to be stable, and each bond consists of 2 bonding electrons. We will start by drawing Lewis structures for simple molecules. Looking at nitrogen trifluoride, we see that nitrogen has 1 atom present in the molecule, and it needs 8 electrons to be stable. We multiply those together, and we get 8. There are 3 fluorine atoms. Fluorine also needs 8, and that gives us 24. We're going to add those up and get a total of 32 electrons needed for stability in this molecule. The available column is using the valence electrons. So again, there's 1 atom of nitrogen. Nitrogen has a valence electron number of 5, so multiplying that together gives us 5. 3 fluorines times the valence electron for fluorine, which is 7, gives us 21. And then when we add that up, we get 26. The first 2 columns are the most important. If you make a mistake on those, we will have errors in the rest of the process. B is N minus A. So we have 32 from N. We're going to subtract A from it. And that's going to give us a total of 6 electrons that are involved in bonds. But remember, a bond consists of 2 electrons. So we're going to divide the 6 by 2. And that's going to give us 3 bonds. L is A minus B. So 26 minus the 6. So not the 3 bonds, but the 6 bonding electrons. When we do that math, we get 20. Again, that's the total electrons involved in lone pairs. But we want to know how many lone pairs there are. So we're going to divide that number by 2, and that will tell us that there are 10 lone pairs. I've circled the 3 and the 10 because those are the numbers that we will actually use when drawing the Lewis structures. When determining the arrangement of the skeletal structure of the Lewis structure, what we need to realize is the least electronegative element is the central atom. This is never hydrogen or a halogen because they can only form one bond. If carbon is present, carbon will always be center. Looking at NF3, nitrogen is the least electronegative element. It is the one that can form the most bonds. So we'll place N in our center as our central atom. We're going to surround it with the 3 F's. We will start on the left, move to the right, and then go down, and then up. So it's left, right, bottom, top is the way we'll place surrounding atoms. Alright, so we need to place our bonds and connect the nitrogen to the fluorines. We're going to have 3 bonds. There's 1, 2, 3. Our lone pairs, of which we calculated 10, we're going to start with the fluorines. So we start with the surrounding atoms and then move to the center. Looking at fluorine, we see that it needs 3 lone pairs to make it have its octet. This fluorine needs 3 lone pairs, and we have our 3 lone pairs here. So we've used up 9 of our lone pairs, and there's 1 lone pair left. We're going to place it on N. We're going to double check that each atom present in the molecule has the number of needed electrons for stability, and in this case, it does. Carbon tetrachloride has 1 carbon. That carbon needs 8 electrons for stability. There are 4 chlorines that need 8 for stability. We add these together for a total of 40. In the available column, we're looking at valence electrons. There's 1 carbon atom, has 4 valence electrons, and then our 4 chlorines each have 7 valence electrons, and that gives us 28. Add those together, we have a 32. N minus A will give us the B, which is the bonding electrons, and we're going to divide that by 2 to get the number of bonds that we will use in our Lewis structure. We are going to then calculate L, which is A minus B, and that gives us 24. And we want to know how many lone pairs, so we're going to divide that by 2, which will give us 12 lone pairs. In this molecule, we have carbon present, so carbon will be our center. And then we're going to surround the carbon left, right, bottom, top with the remaining atoms. We need to make our bonds, and there are 4 bonds, 1, 2, 3, 4. And then our lone pairs. We got to fulfill the octet for each of these surrounding atoms before moving to the center. Chlorine needs a total of 8, and it has 2 present in the bond. So by giving it 3 lone pairs, chlorine will be stable. We then verify that the number of lone pairs that we placed in our Lewis structure matches the number calculated in the L column, and it does. And then as a final check, we want to verify that each atom present in the molecule has the number of electrons needed for stability, and this one checks out. Now we'll take a look at multiple bond molecules. In our first example, there is 1 carbon atom. Carbon needs 8 electrons for stability. There are 2 fluorines. Fluorines need 8 for stability. And there's 1 sulfur that needs 8. Remember, in this column, pretty much all atoms are going to need 8 unless it's hydrogen, beryllium, or boron. Those are the only exception in the N column. So we'll add these together and we get our 32. Looking at the valence electrons, so we can calculate available electrons, we have 4 valence electrons for carbon. There are 7 for the fluorines, giving us a total of 14. And sulfur's valence electron number is 6. Add these together for 24. All right, N minus A gives us a total of 8 bonding electrons, but remember we're going to divide that by 2 so that we know how many bonds there are. 24 minus B, which is 8, will give us 16, and we're going to divide that number by 2 so that we know that there are 8 lone pairs in our structure. Now, looking at the structure of this molecule, we see that carbon is present, and remember that we said whenever carbon is present, it will always be center atom. There are 2 F's and an S, and we want to try for symmetry. So we'll put our F's on the left and the right, and our sulfur at the bottom. The bonds, we said we needed 4 bonds. And remember, this is multiple bond molecules, so it makes sense that even though we connect all of our atoms to the center, we don't have the 4 yet. We're going to have to place a bond on one of these atoms. We know that fluorine can only form 1 bond. It's a halogen. Sulfur, it has 6 valence electrons, so it can form 2 bonds. So we're going to place that additional bond so that we have the 4 bonds needed on sulfur. Now we're going to complete the octets. Looking at fluorine, it has 2 available in the bond, so if we give it 3 lone pairs, it will be stable, and we'll do the same thing for this fluorine atom. Looking at sulfur, we see that it has 2 bonds, so it already has 4 electrons present, so sulfur needs 2 more for stability. We just need to verify that we have the number of lone pairs that we calculated, and then do a quick check or a final check that each atom present in the molecule has the needed number of electrons for stability. The next example is N2, or dinitrogen, also referred to as nitrogen gas. There are 2 atoms present of nitrogen, which needs 8, so we get a total of 16 for that. The valence electron for nitrogen is 5. We're going to take 16 minus 10, and remember that's going to give us the number of bonding electrons, but in order to get the number of bonds, we're going to divide that by 2. We're going to take 10 minus the 6 that we calculated, and that's going to give us 4. And in order to get to the lone pair number, we divide that by 2. When arranging the atoms in the molecule for the Lewis structure, there are only 2 nitrogens, so we're going to place them side by side. We will just use one of them arbitrarily as the central atom when we're referring to it. We have 3 bonds, and the only place those bonds can go is between the 2 atoms present in the molecule. There are 2 lone pairs. Well, each of the nitrogens have 6 electrons present currently. So if we give each one of them a set of lone pairs, now each has the stability of having 8 electrons surrounding it. When drawing Lewis structures for multiple central atom molecules, we're going to see that there are more than one atom that comprise the central atoms. We will do the math, so we'll calculate NAB and L the same way as we have been doing. There are 2 atoms of carbon. Carbon needs 8. That gives us 16 electrons for carbon. There are 6 fluorine atoms. Needs 8. So when we multiply that, we get 48. We're going to add that up, and we have a total of 64 needed. Looking at the valence, carbon has 4, so provides 8. Fluorine is 7, provides 42. And we add that together for 50. We take 64 minus 50, gives us 14. We're going to divide that number by 2, and we'll get 7 bonds. 50 minus 14, or A minus B, will give us 36. Divide that by 2, and we get 18 lone pairs. So we said that we're going to have multiple atoms in the center. We have carbon present, so carbon must be in the center. And we want this to be as symmetrical as possible. So we'll go left, right, and then we'll go bottom. So we've used 1, 2, 3, 4, and we have 2 more to place. So that's what our skeletal structure will look like. We have a total of 7 bonds. 1, 2, 3, 4, 5, 6, 7. And we're going to use up 18 lone pairs. So we're going to look at the fluorines, and we see that they have 2 electrons present in the bond. So each fluorine needs 3 lone pairs. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Do a final check that each atom present in the molecule has the desired or the needed number of electrons, and then you are done. Looking at the next example for multiple central atoms, there are 3 H's in the front and then 3 H's on the end. So let's go ahead and just say that there are 6 H's. Now remember, H was an exception. They don't want 8, they want 2. That's how many they need in order to be stable. We do that math, we get 12. And we see there are a total of 2 carbons. Carbon does need 8. And then there's 1 oxygen, which needs 8. So, when we add this together, we get a total of 36. Alright, so the valence electrons, so they have 6 hydrogens, which have a valence electron number of 1. There are 2 carbons, a valence number of 4. And then 1 oxygen that has a valence number of 6. We're going to add that together and get 20. Then we take 36 minus 20, and that gives us 16 bonding electrons, and that means there are 8 bonds. 20 minus 16 will give us 4 electrons involved in lone pairs, with a total of 2 lone pairs. In this molecule, we have carbon present, so the carbons are going to be our central atoms. I'll place one here, and I'll place one here. We notice that there are 3 hydrogens, and an oxygen left. So looking at this, knowing that it needs to be as symmetrical as possible, it makes sense to put the oxygen in the center so that all three sides on the outside of the carbons are available for the hydrogens. Looking at our bonds, we need to make 8 bonds. There's 1, 2, 3, 4 for that center, and then 1, 2, 3, 4 for that center. All right, so that's a total of 8. Our lone pairs, we only need 2. Remember, hydrogen is done as soon as it makes a bond. It already has the 2 electrons it needs. Looking at each of the carbons, they all have 8 electrons with their 4 bonds. Oxygen is the only one that has a needed amount of electrons. It has 4 right now, so if we place 2 lone pairs on oxygen, it will have the octet it needs to be stable. Again, I constantly encourage you to do a final check of verifying each atom present in the molecule has the stable number of electrons. Now we're going to practice drawing Lewis structures for polyatomic ions. We treat these a little bit differently than the ones we've done previously. When calculating N, we see that there is 1 sulfur atom present. It needs 8. There are 3 oxygens, each needing 8, which gives us 24. We add that together for a total of 32. The sulfur has a valence electron number of 6. The 3 oxygens each have a valence electron number of 6. We add those up and we get 24. I'm putting it there because we have to do some more work here in the A column. This is the available electrons, and we're dealing with a charged atom. We're either gaining or losing electrons, and we have to account for that in the available column. In the example that we have, it's got a charge of 2 negative, which means that it gained 2 electrons. So we're going to gain, which means we're going to add those 2 electrons into our total number of available electrons. For B, we take 32 minus 26, and that is going to give us the 6 bonding electrons, so 3 bonds. Then we take the 26 minus 6 to get how many electrons are involved in lone pairs, and there are 10 lone pairs. When trying to determine the structure, we see that both S and O have 6 valence electrons, meaning they can each make 2 bonds. So we're going to put the one in the center that makes sense. In this case, S makes sense to be in the center so that we can surround it by the 3 oxygens. We're going to connect the center to the surrounding atoms by our 3 bonds that we calculated, and we're going to place our lone pairs starting with the surrounding atoms first in such a way that each atom present in the molecule can be stable. We've used 9 and our 10th will go there. Again, because it's a polyatomic, we're going to treat it a little bit differently. We have to indicate that this is a charged atom. So as we did in our last unit on ionic compounds, we're going to put brackets around the structure and add the charge, which is a 2 negative. Now we can look at our last example of polyatomics, NH4. There is 1 N. It needs 8. There are 4 hydrogens. Hydrogens only need 2. So we have a total of 16 electrons that we need for stability. Our nitrogen has a valence electron of 5. Our 4 hydrogens each have a valence electron of 1. That gives us a total of 9. In this example, our charge is 1 plus, which means we lost 1 electron. We're going to indicate that by subtracting that electron out of our available electrons. And that gives us a total of 8 available electrons for bonds and lone pairs. So we're going to take 16 minus the 8 to determine how many bonds that we will have. And we're going to take 8 minus 8 to determine how many lone pairs we will have. We're ready to draw our structure. Again, looking at the atoms available, we know that hydrogen can never be in the center, so that leaves nitrogen as our center atom. We're going to surround our nitrogen with the hydrogens. And then we need to make our bonds. There are 4 of them that we calculated. There are no lone pairs. We would do a final check to make sure that each atom present is stable. We're going to put our brackets around our structure and add our charge. We're going to end the video by drawing Lewis structures for incomplete octet molecules. This is an exception to the octet. Looking at our first molecule, we have 1B. Remember, B is an exception. B only wants 6 electrons to be stable. There are 3 Fs which want 8. Add those up for a total of 30. B has 3 valence electrons. Fluorine has 7. Add those up. Now we're going to subtract these 2 numbers to get the number of bonding electrons. We're going to divide that by 2 to get the number of bonds. We're going to subtract the 24 and 6 to get the number of electrons involved in lone pairs. And we're going to divide that number by 2 to get the number of lone pairs. For our structure, B will go in the center, F, F, and F. There are 3 bonds that we calculated, and 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 lone pairs. You might be worried that B looks like it needs a lone pair and we don't have any more to give it, but remember, this is an exception to the octet. B only needed 6 electrons to be stable, and it has that with the 3 bonds that it formed with fluorine. So double checking each of the atoms present for stability, we have our Lewis structure for boron trifluoride. Let's look at beryllium dichloride. We have 1 Be, and that is also an exception, only wants 4 electrons, only needs 4 electrons. There are 2 chlorines that need 8, so we get 20 needed. The valence electron for beryllium is 2, for the chlorines is 7, which gives us 16 available. 20 minus 16 is 4. We're going to divide that by 2 to get our bond number. 16 minus 4 gives us 12, and we're going to divide that to get our lone pair number. Beryllium is going to be in the center with the 2 chlorine atoms side by side. We're going to connect it by the 2 bonds that we calculated, and we're going to finish it up by making our chlorines stable with the 6 lone pairs that we calculated. Remember, beryllium only wanted 4, or only needed 4, and it has that with the bonds that it formed. So, thank you for watching this video on drawing Lewis structures.